Hello, pre-cal. So we're here today working more on vectors. Today we're working on assignment 6.3D and E. I know what you're thinking. You're thinking, Miss Patton, why do you keep stacking up two on top of each other? Well, this time the answer is because 6.3D is so easy that we could almost just skip it. But I don't want to skip anything, so we're going to do it, but you're going to find it really, really easy to do. So here's how operations on linear combinations work. What's going to happen is they're going to give you two vectors. In this case, I've got vector u is vector I plus vector j, and vector v is 5i minus 3j. And the question is, what is 2u minus 3v? Well, this works exactly the way you would think it would work. You are just going to substitute your u vector and your v vector into your expression. So I replaced u with I plus j, and I replaced v with 5i minus 3j. And now we've already studied distribution. That was in our properties the other day. We know that distribution holds up. So if I simplify this, I can distribute this 2 scalar into my I and j vectors. I can distribute this 3 scalar into the 5i and the 3j, paying real close attention to my signs. That negative 3 needs to go with that scalar. So when I do those distributions, I've got 2i plus 2j minus 15i plus 9j. And so now if I put all of my I vectors together and all of my j vectors together, I get negative 13 in the I direction plus 11 in the j direction. That is literally it. So I'm going to give you 5 or 6 problems to do like that, but you are going to breeze right through them. There is not much to it at all. Remember, I is your identity vector that goes 1, 0, and j is your identity vector that goes 0, 1. Your unit vectors in those directions straight along your axes. So keep that in mind as you're working. Okay, so the real meat of what we need to talk about today is direction angles. This is coming out of 6.3E. And so what we have to do now is take what we learned about vectors and mash it with, oh, are you ready for this? It's my favorite thing, the unit circle. I know those things don't seem related at all to each other in your mind at this moment, but there's actually a very cool connection. Because if u is a unit vector, then doesn't that mean it's going to wind up landing, its terminal point is going to land on the unit circle? Let's call all these places my 1s and negative 1s. And so if I have some random u that I know is a unit vector, that terminal point is always going to land on the unit circle. Now I've drawn it in the first quadrant, but obviously it could be in any quadrant. And what do we know about the components of this vector? Well, they're going to have to line up with those points on the unit circle. And so that x component is going to be cosine of our direction angle. This angle in here now, we called it the reference angle when we were talking about unit circles. Now we can call it the direction angle. It describes the direction of our vector. We usually use a theta for that. And so the x component is going to be cosine theta, and the y component is going to be, that's right, sine theta. And so now all of our vectors can be expressed in terms of sine and cosine. So all of that trig that you just learned actually has a purpose, and that purpose, one of those purposes, I suppose I should say, is really tied up in the study of vectors. All right, so here's an example of what they might ask us to look at what they might ask us to do with this cosine and sine idea built in. So the first thing that I want you to think about here is if I have a vector v described as 3 cosine theta in the I direction and 3 sine theta in the j direction, what would that make the magnitude of v? What would that make the magnitude of v? So, how do we find magnitude? Let's remember that magnitude of any vector is there. It's like the distance formula, right? The change in x squared plus the change in y squared, if we're talking about a unit vector in standard position, right? We just use the components. So, what is my x component? Well, it's this 3 cosine theta. And what's the y component? Well, it's this 3 sine theta. So, how does this simplify? Nine cosine squared theta plus 9 sine squared theta. Okay, now we're going to factor out a common factor. So what do my two pieces have in common? Well, they both have a 9. Hopefully you're getting that little red flag in your brain going off saying, hey, I know what that is. I know what that is. I should know what that is because cosine squared plus sine squared is always 1. And so this simplifies to the square root of 9, which means my magnitude is 3. Look at where that 3 showed up in our initial setup of our problem. It does not matter what theta was. Theta could be 10 degrees, it could be 100 degrees, it could be 330 degrees. It doesn't matter what theta is. When I work out this magnitude every single time, it's going to match that coefficient out front if they are the same, which allows us to maybe use that information to build vectors of our own that meet certain criteria. Okay, so now using that idea, now I can work the other direction. Now I can figure out the direction angle if I have the vector. All right, so I can think about this in a couple of ways. The direction angle is always easiest to do with a unit vector. Could I do it without the unit vector? Yeah, I could. But all of my personal knowledge is wrapped up in that unit circle. Sine and cosine are so much easier to deal with on the unit circle. And so, that's what we're going to do. We're going to use the unit circle to help us out of these situations. Okay, so we need a unit vector that goes this same direction. Well, you already know how to do that. To find a unit vector, we take our vector and we divide it by its magnitude. So my components would be 3, 3. I find components easier to deal with when I'm doing this particular calculation. You wouldn't be wrong to write it with the i's and the j's. It doesn't matter. It's the same calculation. And then we're going to do the square root of 3 squared plus 3 squared. That's how we would calculate our magnitude. If I was going to write it with i's and j's, it would look like this. So what do we have? Well, 9 plus 9 is 18, so that denominator is the square root of 18. So I'm going to say 3 over the square root of 18i plus 3 over the square root of 18j. So this is a unit vector. Which means it is on the unit circle. So this component describes the x-coordinate of a point on the unit circle. And this coordinate describes the y value of a point on the unit circle. So we need to figure out what angle lands us on this point. So we need to figure out cosine theta is 3 over the square root of 18. We need to figure out theta. Now at first glance it might not seem like you know the answer to this, but with some simplifying here, you're going to realize that this 3 over square root of 18 is actually a much nicer thing to deal with, because 18 is 9 times 2, so 3 times 3 times 2, which means I can rewrite this as 3 over 3 root 2. My 3's divide out to 1's, and then if I rationalize, I get the square root of 2 over 2. So for what theta value is cosine square root of 2 over 2? Well, because we know our unit circle, we know that this point is the root 2 over 2, root 2 over 2, right? And then we know this one down here is also going to have root 2 over 2, negative root 2 over 2. So it's got to be one of those. How do we figure out which one? Well, we go and we look at the sine value. So this sine theta is also 3 over the square root of 18. Their signs match. And so the only place that the signs match would be in the first quadrant. So there's my direction angle. My theta is, what is that? It's pi over 4. Could I have done it in one step instead of in 2 steps? Yeah, you can. What trig function do we know that uses sine and cosine? We know tangent. So I could say tangent theta is, and then pull the sine value, 3 over the square root of 18, over the cosine value, which is 1. Well, where is tangent 1? At pi over 4. How do I know I don't want this one in the third quadrant? Because there's another tangent that's 1 in that third quadrant, right? How do I know which one to pick? Well, when I look at this vector, I've got a positive and a positive. So it has to be in the first quadrant. It cannot be the one in the third quadrant. So sometimes it's easier to just use tangent to begin with than it is to split it into 2 pieces. Okay, I'm going to give you a couple to try. Let's see if you can find the direction angle for a couple of vectors. So I'm going to put these on. You're going to pause the video. You're going to go do your work, and then you're going to come back and check your answers. Alright, so you're going to pause the video. Try those two. Find your direction angles, and then come back here to check your work and get some final instructions.